can't get any faster or simpler either. I mean, for each memory allocation, we're basically just moving one pointer around and adding, doing an integer addition. I mean, there's no way we can get any faster in the general case. And there's no bookkeeping overhead worth mentioning. We don't need to have information about the free blocks and stuff like that, because we're just allocating stuff in turn and have a current allocation pointer, and that's pretty much it. And you don't have to delete stuff at all. You just call this reset every frame, which resets the current allocation pointer, and that's all the deleting you have to do. So you actually save some code to write. Things allocated after each other get memory next to each other, which is a nice property if you have, for example, a 3D engine. You usually visit objects in an order that has some geometric significance. You usually visit things next to each other that are geometrically close. If you do things like, well, some culling based on lights or visibility checks, chances are good that stuff that is geometrically close will be either all visible or all invisible or stuff like that. And so this will mean that after you do this allocation procedure, this will be continuous blocks of memory you won't even touch, which is nice. So this gives us nice cache behavior. Of course, it's not all that simple. The biggest limitation of this strategy is that it's really limited to objects that have a lifetime of only one frame. So we really can just use this for stuff that's being allocated and destroyed every frame, which is perfect for the type of data I discussed. But obviously, most of the data you have in your program doesn't work that way. Now you're not limited to that frame. You can call reset however often you want. You can call it, say, once every scene change or stuff like that. But still, it's a pretty limited policy. And similarly, you can't use this in C++ when your objects have constructors or destructors. I mean, you could manage so that constructors get called, but the problem is, by the point you're calling reset, you don't know what type of memory was allocated to whom. You don't know which destructors to call. So there's really no way to make this work with this simple or simplified strategy. So you have to live with that you can basically just use plain data structures without any functionality and just bytes you're copying around. And there's also a static maximum amount of memory you can use, which is the value you pass in as you initialize that memstack class. I mean, this can be fixed relatively easily. You can just include some logic to test if you're already at the end of the buffer, and if so, open up a new buffer of another size, whatever. So you can work around this. But it makes things more complex and is not really relevant to the general idea, so I kept it out of the slide. And it's also only usable for small data structures, because if you're allocating large amounts of memory, say a few hundred kilobytes each allocation, that's not worthwhile, because you have to make your buffer you take those allocations from very large to make sure you don't overflow. And most of the time, that buffer will probably not use completely. So you're wasting huge amounts of memory, for no good use. So you want to avoid that. In conclusion, this is a technique that's not usable everywhere, but it's really so simple. You can always just try it out, because when it works, I mean, it doesn't get any simpler than that, it doesn't get any faster than that, so you're basically, all happy. I mean, you can't get any simpler than that. Next topic is, and last topic actually, is about sorting tricks. This usually crops up in a lot of places. You need some sort of sorting. And don't worry, I'm not going to start a usual CS lecture now. This is not about fundamental sorting algorithms. This is about the stuff you usually don't hear about in general, or classic algorithms texts, or in CS classes. Those have some different properties than the ones you usually see. First off, and most importantly, they're not comparison-based at all. You're not using comparison. So you are able to get linear running time. So you just visit each item, a fixed number of times, and that's not dependent. The number of times you visit the item is not dependent on how much data you're sorting, which is in contrast to classic sorting algorithms, which, visit multiple times. But these algorithms don't always give you a correct solution. They don't always give you a correctly sorted, list. And so what the heck is incorrect sorting good for, you may ask? Because, well, if I get an incorrectly sorted list, what is that supposed to mean? Well, you get correct sorting up to a certain tolerance. So the difference between items next to each other isn't more than a certain maximum value. So you don't have things that are really far off from where they should land, but it's just a little bit off. And in some cases, for example, there's no easy way to determine a correct sorting order anyway. For example, when you're Z-sorting triangles, because you want to paint them in some order, no matter what you do, what value you sort by, middle point of the triangle, whatever, there will always be cases that don't work correctly. And so no matter which criterion you pick, you'll always have to fix up things afterwards. So it doesn't really matter if your sorting algorithm you use isn't completely correct, because you have to fix it up anyway. And if you don't, you don't care about it. And also sometimes it's not critical things are perfectly sorted. Because, for example, when you're sorting by the material in a 3D engine to minimize the amount of material changes you do, which is a good idea on current graphics cards, well, it's obviously nice if you have the minimum amount of material changes possible, but if you happen to have a few more than are strictly necessary, this is not a big problem. I mean, you would like it, you would like it if it was otherwise, but this is not going to be a huge problem for you. So this is also a case where you can make do with imperfect sorting. And the type of algorithm I'm talking about is the simple algorithm I'm talking about is called ordering tables. This name originates, to my knowledge, from the Sony PlayStation 1. Maybe wrong there, but it doesn't really matter. And the PlayStation 1 is a very interesting piece of hardware to look at, because, well, it has support for hardware rasterization. It can render triangles, although completely without perspective correction, and also, well, by today's standards, laughable accuracy. But it was able to render triangles in hardware. It had a very simple fixed point vector unit, but which you really needed because the main CPU you had was clocked at 33 megahertz. So you really had to make sure, you used all your computing resources efficiently. And this PlayStation also had no Z-buffering support at all. So if you wanted things to appear in the correct order on the screen and not have any sorting problems, you had to sort the triangles yourself, which is not exactly what you want to do when you have a 33 megahertz CPU. I mean, you have to build up your triangle list and stuff like that every frame, and you really don't want to be touching the data again and again and again. So luckily, the PS1 engineers had a very nice solution, which is called ordering tables. Well, what you do is very simple. You divide your Z range, your coordinates, whatever depth, into n equal sized parts, and have an array with n elements, which is the ordering table, that are just pointers to those polygons. And your polygon also has a next field, next polygon. And every frame, you clear that array to 0, which means there are no polygons to paint. So that's where you start off. And for every triangle you want to draw, you first calculate the corresponding index, I, which is the point you insert into the list. As said, this is equal size parts in that, so you basically do just some multiplying and some dividing, and then you know where it should end up in the ordering table. And then you insert it into that point in the ordering table, like with a linked list.